650 light-years away sits one of the most iconic structures in the cosmos, the Helix Nebula, a dying star's final breath. But on January 20th, 2026, Webb zoomed into this edge and saw a storm. On the screen right now, it looks like a storm of comets, thousands of glowing heads with long, streaming tails, frozen mid-fall inside a dying star's death shroud. But here's the twist. These aren't comets at all. NASA's Webb mission team explained in their January 20th, 2026 release that this is a close-up of the Helix Nebula, an expanding shell of gas and dust shed by a dying star, and that the comet-like shapes are knots and pillars being sculpted as fast hot winds crash into older, colder shells. The star that made all of this has already collapsed into a white dwarf, and it sits at the heart of the nebula, actually out of the frame of Webb's zoomed-in shot. So what exactly are we looking at? Why does a dead star's final breath break into a blizzard of comets? And why are astronomers treating this one image like a time machine for our own solar system's future? Because the Helix Nebula is close. NASA's official Webb image page lists it at about 650 light-years away in the constellation Aquarius. And that proximity turns Webb's infrared eyes into a microscope. In this single field, only about 1 light-year across, Webb is catching a boundary where physics changes, where blazing ionized gas gives way to cooler molecular hydrogen, and where dust can shelter chemistry complicated enough to matter for future planets. Tonight, we're going to do something simple and unsettling. We're going to treat this storm of comets as evidence. We'll zoom out and locate the scene. We'll zoom back in and read the shapes like forensic marks in a crash site. And we'll see why the helix is a death shroud, but also a factory flaw. And by the end, the question won't be, what is Webb seeing? It'll be, what does it mean that this is the fate of sun-like stars, and the raw material of whatever comes next? Let's start with what Webb actually saw. The Helix Nebula is one of the closest and brightest examples of a planetary nebula, an object created when a sun-like star runs out of fuel, swells, and then sheds its outer layers into space. ESA's January 20th, 2026 photo release calls the Helix one of the most iconic planetary nebulae because of its striking ring-like shape, and it notes that astronomers have been studying it in detail since it was first spotted in the early 1800s. NASA's Caldwell 63 catalogue page gives the Helix a sense of scale. The bright inner ring is nearly 3 light-years across. And that's not a tiny bubble. That's a shell large enough to swallow our entire neighborhood of nearby stars. And yet, Webb is not showing you the whole eye. NASA's January 20th, 2026 Webb article includes a context image from the ground-based Vista telescope with a box marking Webb's field of view. The boxed region is a thin slice along the inner rim of that ring, like zooming into the edge of a hurricane and finding it made of individual, glowing raindrops. In Webb's image, NASA says, color is doing double duty. It's telling you both temperature and chemistry. A hint of blue marks the hottest gas, energized by intense ultraviolet light from the central white dwarf. Farther out, the scene turns yellow where hydrogen atoms join into molecules, and at the outer edges the reds trace cooler material where gas thins and dust can take shape. And that last part matters, because it's where the story stops being only about death. NASA's Webb team points out that the same radiation that strips electrons and heats gas can also leave protective pockets within dust clouds, shielded zones where more complex molecules can begin to form. Spitzer hinted at that chemistry years ago, NASA notes, but Webb's resolution makes it visible. Look for the dark pockets amid the glowing orange and red. So the death shroud is layered. Closest to the star is a harsh zone of ionized gas, blasted by ultraviolet. Farther out is molecular hydrogen, cooler, denser, and more fragile. And threaded through the boundary are these comet-shaped knots, thousands of them, etched into the shell like an impact pattern. And now we can ask the first real question. If this is just gas being thrown off into space, why does it break into comets at all? To understand that, we have to be careful with the word comet. Real comets are icy leftovers from the early solar system, small bodies on long orbits that grow tails when sunlight heats them. What Webb is showing is different. These are dense clumps of gas and dust embedded inside the nebula itself. NASA's Caldwell 63 page describes them as cometary knots, and it gives a jaw-dropping scale. Some of the heads are at least twice the size of our solar system, and the tails can stretch about 100 billion miles, over 1,000 times the Earth-Sun distance. So when the word storm is used, it's not exaggerating the count. It's exaggerating the feeling of motion. These structures are huge, and they're everywhere. Astronomers have been tracking them for decades. A Hubble Space Telescope overview of the Helix Nebula points out that these cometary knots were first discovered in 1996, and it describes them as dense, gaseous masses with tails pointing away from the hot central star. NASA's own Astronomy picture of the day, entry from April 13, 2008, emphasizes the mystery. The knots show up not just in the helix, but also in other planetary nebulae, and their origins were not initially predicted. In that same explanation, APOD notes that the knots can have masses similar to Earth, while spanning radii several times the orbit of Pluto. So you're looking at planet-scale mass packed into a cloud the size of a miniature star system. Webb changes the conversation because it sees them in infrared with brutal clarity. You're on NASA's Webb image page for the Helix Nebula. The listed instrument is NIRCam, and the filters include bands that target, among other things, molecular hydrogen emission. The result is that the knots and their tails don't just appear as fuzzy silhouettes. They appear as structure, like the grain in wood or the ripples in wind-blown sand. And structure is a clue, because these knots are not randomly oriented. In Webb's January 2026 article, NASA notes that the pillars trace the circumference of the inner region of the expanding shell, and that their extended tails all stream away in the same general direction, aligned with the central star's radiation and winds. That's the signature of sculpting. Something is hitting these clumps. Something is burning into them. And whatever survives, it survives because it is dense enough to resist being erased. So where do the clumps come from in the first place? And this is where Webb's just saw part becomes important, because the helix has been photographed for a long time. NASA's January 2026. Webb release makes the comparison explicit. Webb's near-infrared view brings the knots to the forefront compared to an ethereal visible light image from Hubble, while Webb's higher resolution sharpens details beyond what Spitzer could show in infrared. That's not a knock on Hubble or Spitzer. It's about what each telescope is tuned to detect. Visible light emphasizes the glowing, ionized gas, the parts of the nebula directly lit up by ultraviolet radiation. That's why classic Hubble views look like delicate, blue-green arcs and filaments. They are tracing emission from ions in hot gas. But the knots are partly about what survives in cooler, denser regions. Infrared light is better at tracing that cooler material, including molecular hydrogen and warm dust, exactly the ingredients NASA highlights in the helix. Hot ionized gas near the white dwarf, cooler molecular hydrogen farther out, and dustier, colder edges. So when Webb looks at the helix, it's almost like switching from photographing a bonfire to photographing the smoke and embers. Suddenly, the empty spaces aren't empty, they're structured, and the knots stop being background texture and start being the main event. That shift also changes how the helix can be studied from Earth. NASA's Caldwell 63-page notes that the helix is visible in binoculars and small telescopes as a faint, hazy patch, and that dark skies help because it's diffuse. In other words, and to our eyes, the helix is a gentle glow. To Webb, it's a coastline made of cliffs. That contrast between what human vision sees and what infrared reveals is why the helix keeps returning as a test object for new telescopes. Each new wavelength peels back a different layer of the same story, and Webb's layer is the one where the storm appears. This is where the Helix Nebula stops being a pretty picture and becomes a physical experiment. Imagine a star like the Sun in its final act. For most of its life, gravity pulls inward and nuclear fusion pushes outward. But when the core can't fuse fuel efficiently anymore, the balance breaks. The star swells, loses mass, and dumps huge amounts of gas and dust into space. Then the remaining core becomes exposed, hot, compact, and ferociously bright in ultraviolet. And that ultraviolet turns the surrounding expelled gas into a glowing nebula. The planetary nebula phase is brief by cosmic standards. A NASA Hubble explainer from 1997 notes that a typical planetary nebula glows for around 10,000 years before it disperses into the interstellar medium. That means every planetary nebula we see is a snapshot, an instant in a star's biography. Webb is staring into one of the nearest snapshots we have. In NASA's January 2026 Webb article on the Helix, the mission team describes the key action. Blistering winds of fast-moving hot gas from the dying star are crashing into slower-moving colder shells of dust and gas that were shed earlier, sculpting the nebula's structure. That collision is a recipe for chaos. You can think of it like a cosmic sandblaster. A fast flow slams into older material. It piles up, it compresses, it rips into weak spots. And if the shell isn't perfectly smooth, if it contains denser patches, those patches become the seeds of pillars. That seed idea shows up explicitly in the scientific literature. In their 2004 paper on the Helix Nebula, C.R. Odell and collaborators summarize a scenario where the knots are formed in or near the local ionization front, and then sculpted by stellar radiation as the ionization front advances beyond them. In other words, the clumps are born right at the boundary where ultraviolet light first bites into the gas, and then the star's radiation carves tails behind them. This also matches the way Webb's image reads as layers. NASA describes hot ionized gas closest to the white dwarf, cooler molecular hydrogen farther out, and dustier, cooler zones at the edges. And if the knots form near that shifting boundary, where ionized gas meets molecular gas, then it makes sense that Webb sees them exactly where it does, tracing the inner rim like a fringe. But there's an important honesty check here. Astronomers do not claim the knot origin is solved. Even NASA's APOD entry from 2008 says their origins are still not well understood and presents hypotheses rather than a single verdict. The helix is teaching us, but it's also reminding us. Nature is allowed to be complicated. One reason it's complicated is that the helix itself is complicated. Odell's 2004 work describes the helix's main ring not as a simple, flat disk, but as a more complex structure with multiple components. And it notes that knots begin to be observed at about the distance where the highest ionization core gives way to lower ionization zones. That's exactly where you'd expect the ionization front to matter most. And another layer of complexity appears in a 2005 monthly notices of the Royal Astronomical Society analysis by Meeburn and colleagues. Their study compares Helix observations to the classic interacting two-winds model of planetary nebula formation and argues that only after the fast wind has switched off could the observed global velocity structure be generated. They also suggest that the clumpy nature of the material could help create radial spokes that may actually be persistent tails of cometary globules whose heads have now completely photo-evaporated. Read that again. Heads can be erased. Tails can remain. And so when you look at Webb's storm, you might be looking at a survival story in progress. Some knots are still dense enough to keep their heads bright, compact, resisting the blast. Others may already be in the process of dissolving, leaving behind only the faint, stretched-out shadows of what they used to be. That's why Webb's view feels so alive. It's not just a nebula. It's an active demolition site, and we're catching the demolition mid-swing. Now, let's slow down and really read what the comets are telling us. On NASA's Webb image page, the Helix Nebula field is described as about 5.6 arc-minutes across, roughly 1 light-year at the nebula's distance. And the data are listed as NIRCam observations taken on October 24th, 2024, and released publicly on January 20th, 2026. That means what you're seeing is not an artist's impression. It's a measurement. Look at the heads. They're brighter, denser, and they sit on the rim like beads on a wire. Then from each head, a tail stretches away into darker space. Hubble descriptions of cometary knots emphasize that their tails point away from the hot central star, and NASA's 2026 Webb article describes them as pillars with extended tails along the circumference. Again, all aligned with the same central source. That is exactly what you'd expect if radiation is doing the carving. Ultraviolet light slams into a dense clump. The clump's surface heats, ionizes, and begins to evaporate. Gas streams off the illuminated side, and the flow is swept back into a tail. In planetary nebulae, this is a known kind of shape-making, a bright, dense head with a shadowed wake. But Webb adds a crucial detail: where the tails live. The NASA says the Webb colors trace a transition from hottest gas to coolest gas as the shell expands outward from the central white dwarf. So the tails aren't just blown back. They're embedded inside a thermal gradient, a boundary layer where conditions change fast. And that boundary layer is where chemistry changes too. In NASA's January 2026 context description, the team spells it out. Hot ionized gas closest to the white dwarf, cooler molecular hydrogen farther out, and dust clouds that can shelter protective pockets where more complex molecules begin to form. Those pockets show up as darker gaps in the glow. So these knots are not just debris. They are shields. They are tiny fortresses of density inside a hostile ultraviolet flood, creating microenvironments where molecules can survive long enough to do interesting things. And this is the part of the story that doesn't get said out loud often enough. A dying star isn't only destroying, it's sorting. It's separating the material that gets shredded instantly from the material that stays dense, cool, and chemically rich. And that sorting decides what the interstellar medium receives when the nebula disperses. In other words, the storm of comets is a delivery system. But delivery of what? To answer that, we need to zoom out from the knots and look at the star that made them. Helix Nebula looks calm from far away. From a distance, it's an eye in the sky, so much so that NASA's January 2026 Webb article notes its resemblance to the Eye of Sauron, And the helix has also been nicknamed the Eye of God in popular culture. But the eye is an illusion of perspective. And what we're really seeing is geometry, rings and shells, almost face-on. NASA's Caldwell 63 description calls it a planetary nebula with a prominent inner disk, and it emphasizes that the central star is still visible in the middle. ESA's 2026 photo release also frames it as a chance to study the final moments of a dying star in extraordinary detail. In NASA's Webb context text, the central object is described as a blazing white dwarf, the leftover core of the dying star, sitting right at the heart of the nebula, out of the frame of Webb's close-up. That core is the engine. Its radiation is what makes the shell fluoresce. Scientific studies go further. In the 2004 analysis by Odell and collaborators, the helix is treated not as one simple ring, but as a more complex structure, and the authors describe how the knotty features emerge at specific distances from the star, tied to changes in ionization conditions. They also adopt a distance based on trigonometric parallax work, giving a physical scale that turns arcseconds into trillions of centimeters, a reminder that every hair in this image is enormous. And in the 2005 Monthly Notices study, Meeburn and colleagues summarize literature estimates that place the central star, WD 2226-210, at an effective temperature around 117,000 Kelvin, with a mass around 0.93 times the Sun. Whether or not those exact values shift with later analyses, the qualitative reality stands. The remnant core is blisteringly hot, compact, and capable of blasting ultraviolet light into everything around it. That ultraviolet does two things at once. It makes the nebula glow by ionizing gas, and it tries to erase structure by heating and evaporating dense clumps. So the helix is a competition between expansion and erosion. Gas is racing outward because it has been thrown off the star. At the same time, radiation and winds are chewing through it from the inside out. Wherever the shell is smooth, it thins and fades. Wherever the shell is clumpy, the clumps become targets, and the survivors become knots. This is why the comet's shapes feel like they're pointing somewhere. They are pointing back to the source of the violence. But here's the deeper consequence. According to NASA's January 2026 Webb article, this whole process is literally recycling. Stars returning their material to the cosmos, seeding future generations of stars and planets. The helix is not a dead end. It's a transfer of material from one generation to the next. That means the knots are not just sculptures, they are inventory. They are stored mass, stored dust, and stored molecules, packaged in dense, shielded pockets, waiting to be mixed into the interstellar medium as the nebula disperses over the next several thousand years. So let's connect the dots. If this is a preview of the eventual fate of a Sun-like star, as both NASA and ESA emphasize in their 2026 releases, then this storm of comets is a preview of the kind of environment that may one day surround a star like ours. A hot remnant core, an expanding shell of ejected material, and countless dense clumps being carved into tails by radiation. And here's the part that should genuinely change how the image feels. Those clumps are where the next story can begin. And because chemistry does not happen best in the blazing center, it happens in the shadows. NASA's Webb context description is unusually direct about what the colors mean. The blue-tinted regions are the hottest gas, energized by ultraviolet light from the white dwarf. The yellow regions mark gas cooling enough that hydrogen atoms can join into molecules, and the reds trace the coolest material where dust can take shape. That sentence is quietly radical, because it means Webb isn't just showing where stuff is, it's showing what state the stuff is in. and the state decides what the cosmos can build. In the bright blue zone, atoms are stripped and heated. Chemistry is hard to maintain. In the yellow zone, molecular hydrogen appears, H2, signaling cooler, denser conditions. And in the reddest outer edges, dust becomes more significant. Yin and dust is where shielding happens. A dense grain can block ultraviolet, creating a shadow. Enough shadows overlapping, and you get pockets. NASA explicitly calls those protective pockets, and it links them to the formation of more complex molecules inside dust clouds. It also notes that Spitzer's studies of the helix hinted at this chemistry, but Webb's higher resolution shows how it forms in shielded zones, visible as dark gaps amid the glow. So, in a very real sense, the Helix Nebula is drawing a map of survivable chemistry. The knots and their tails are part of that map. Their heads are dense enough to hold onto material, and their shadows can carve out colder regions behind them. You can almost read the nebula like weather radar. Bright returns where gas is hot and glowing. The darker voids where dust and density hide what's inside. This is why infrared is such a powerful choice. On NASA's Webb image page, the Helix observations are listed as NIRCam data, taken through a set of filters that includes narrow and medium bands like F187N, F212N, and F470N. ESA's detailed image release for the Helix lists those same filters and associates them with specific physical tracers, like Passion Alpha for hydrogen and molecular hydrogen lines, so the final composite becomes a chemistry-coded photograph rather than just a pretty palette. And it leads to a strange realization. The death shroud is not uniform. It's patchy, it's textured, it's full of refugees, which means the material a star returns to the galaxy is not a smooth mist. It's structured. It's delivered as filaments, knots, in undusty pockets, some of which may carry a richer chemical toolkit than others when the nebula finally dissolves. That brings us to the biggest question hiding underneath the title. If these aren't comets, why does the metaphor work so well? Because comets, in our own solar system, are time capsules, preserved material from the early days. And these knots are also time capsules. They are preserved material from the final days. They are the parts of a star's lost envelope that are dense enough to resist destruction, long enough to be repurposed. And as NASA and ESA both emphasize in their 2026 releases, that repurposing is not abstract. It's literally the seeding of future stars and planets. So the image isn't just about a star dying, it's about a star refusing to disappear cleanly. It's about a star leaving behind structure, and structure is what the universe uses to start the next cycle. And that cycle has a personal edge. Because NASA's Webb article frames the helix as a possible eventual fate for our own sun and planetary system. That doesn't mean the helix is a perfect prophecy. Every star has its own mass, companions, and environment. But it does mean the broad pattern is relevant. A hot remnant core, an expanding shell, and a final moment where the star's last breath becomes the raw ingredients for whatever comes after. So when Webb shows you this storm of comets, it's really showing you the boundary between endings and beginnings. A death shroud that is also a nursery. A demolition site that is also a supply chain, and a reminder that the universe doesn't waste its materials, it just changes their form. And if you want to see cosmic recycling with your own eyes, it's hard to imagine a clearer snapshot than this. A 1 light-year wide slice of the Helix Nebula, only 650 light-years away, packed with thousands of comet-like knots, each one a dense packet of matter being carved, sorted, and prepared for the next chapter. That's what Webb just saw. not a storm of comets falling into a star, but the storm a star becomes when it dies.